Welcome back. Motor driver circuits. If you are interviewing with a robotics company or any sort of company that is doing some sort of electromechanical project, you are definitely going to get a question about how a motor is supposed to be driven. Let's think about this. We've got, let's say, a DC brushed motor. How do we actually get this motor to drive from, let's say, a battery source? Well, we could just connect the battery directly to the motor, but then it's just going to dump all of its energy into it and never be able to turn on and off. So we have to actually put some sort of switch in between the motor and the battery. But then the motor can essentially only be turned on full and turned off all the way full. So that's a problem. Another problem is that the motor can only turn in one direction versus the other direction. So how do we actually design a proper motor driver circuit? Well, the best and easiest motor driver circuits for DC brushed motors is known as a H-bridge. And this will be the foundation of the interview question that we're going to ask right now. Using a 5-volt logic microprocessor, so think Arduino, with only 2 remaining general purpose input-output pins that each have up to 100 milliamps of current sourcing capability. Draw a driver circuit for a brushed DC motor that must be able to rotate in both directions, forward and reverse, running off of a 5-volt battery that doesn't sag. All right, so an ideal 5-volt battery. So basically what they're saying is you've got this Arduino, let's call it a microcontroller, that runs off of 5 volts, and it only has 2 GPIO output pins remaining. GPIO, general purpose input-output pin. These are digital pins. We'll label them A and B. Basically, the question is how, using just these 2 pins that each have 100 milliamps of current sourcing capability and swing up and down to plus or minus 5 volts, how can we drive a motor that's DC brushed, meaning it only needs a single voltage applied across its terminals, that runs off of a 5-volt battery. So we'll call this a 5-volt battery. And the battery is ideal, so it maintains its voltage regardless of what you're doing to it. And of course, as we previously mentioned, we're going to talk about how to implement an H-bridge circuit to this. So what I'm going to do is erase all of this and give you the answer, and we are just going to identify how this works. So the answer is to design a circuit that looks like this. There's a 5-volt battery over here that supplies power to the top terminal here, and the other terminal is ground. There's a motor in the middle, and its leads are connected to a node here and a node here. The motor's nodes are connected in between 2 transistors. The top transistor is a P-type transistor denoted by the circle over here. Same with this one. And the bottom transistor is a N-type transistor. Now this is the simplest and easiest type of H-bridge, where the top transistors are P and the bottom are N. It is possible in certain H-bridges for you to have N-type transistors on the top. But for the purposes of this question, we've made it easy by saying that the battery is 5 volts and the 5 volts on the microprocessor is able to provide 5-volt logic, meaning that we can turn on and off all of these transistors perfectly with 5 volts. Basically, we have 2 inputs, A and B. Now, in order to drive the motor in this direction, have current flowing through it in that direction, current has to flow from the top here through the motor and down this bottom transistor, the bottom right one. And in order for current to flow the opposite direction, right to left, current has to flow from the top right p-type transistor through the motor and down through the n-type transistor. We know that in order for the p-type transistors to turn on, their source to gate voltage, VSG, must be negative. And in order for an n-type transistor to turn on, their VGS must be positive, greater than their threshold values. We'll assume for the purposes of this exercise that the threshold values of these MOSFETs is all much less than 5 volts. Therefore, if A was high and B is low, that means that this transistor would be on, this transistor would be off because VSG would be 0 since the source of the PFET is connected to 5 volts, and A would also be 5 volts if A is high, therefore VSG is 0, so this transistor is off. The source of this bottom transistor is connected to ground, and if its gate is high, or 5 volts, then it will be on. If B is low, then the opposite happens on the right-hand side. This transistor is on, and this transistor down here is off. So current will flow through the green direction. Now, if A is down, A is low, and B is high, the opposite will happen. You'll have current flowing through this top transistor, top left, through the motor, and down through this bottom right transistor. So this is the easiest way that you can use only 2 remaining GPIO pins to drive an H-bridge circuit. However, H-bridges sometimes can be, as I mentioned previously, with only using NFETs and having the motor in the middle here. Now, the problem with only having NFETs is that you cannot control their gates the same way that we've controlled the gates over here. The problem becomes how to turn on the top side MOSFETs, VGS, of the top side MOSFETs. Because if you simply apply, let's say, a 3.3 volt signal to the gate of the resistor, the gate of the transistor, that doesn't actually mean that the gate to source voltage of the transistor will be 3.3 volts. And therefore, the transistor may not turn on because its source voltage might be up high since the motor is turning. So what you do need is a gate driver circuit that has a higher voltage and can sense the source potential and apply a gate to source voltage that can turn on and off these transistors. That's why during interviews, I typically don't ask a question about how to drive higher side and channel MOSFETs, and I give people a really simple interview question about motor driver circuits with 5-volt logic processors and a battery that also runs off of 5 volts. But the truth is, in real life, most batteries are at much higher voltages than the logic that we're using to drive the transistors, and therefore we need special integrated circuits to drive higher voltages into the gates of these transistors to assure that they turn on and off properly. But this circuit, again, is known as an H-bridge. It's H because it kind of looks like an H. H. And an H-bridge allows you to drive a motor, a DC brushed motor, in both directions, forward and reverse. And in this specific example, because a MOSFET takes so little gate current in order to drive its gate voltage up, a 100 milliamp current sourcing capability of the GPIO pins allows you to directly connect the gate of these MOSFETs to the Arduino that we previously designed. So when you go into an interview, make sure you really understand how H-bridges work and how to drive a DC brushed motor. We'll talk later about how to drive a DC brushless motor, which essentially needs 3 phases of power, and what it really ends up looking like is 3 of these half bridges controlling one controlling each phase of a DC brushless motor. It just gets a little bit more complicated. But make sure if you're going to a robotics company or any company working on electromechanical products that you truly understand how motor driver circuits work, how you would, for any given application, drive a motor. Now, the next question you may have is, well, Arya, you told me that just being able to turn on and off a motor is not enough. We also have to be able to control its speed. While that isn't part of this question, we really should talk about it. How do we actually control the speed of a motor? Well, we can use what we learned in the previous section about pulse width modulation. Instead of just driving these gates either high or low, we can drive them high and low very quickly over time in order to get an average duty cycle, an average effective voltage at the gate that turns them on and off very quickly, so you have a lower amount of current based on the duty cycle. A motor's current is directly proportional to its torque, and the voltage that's seen across a motor on average is also directly proportional to its speed. So if we PWM the gates of these MOSFETs with the appropriate duty cycles and at the appropriate frequencies, then we can control the speed of a motor. All right, that concludes this lecture. In the next lecture, we're going to talk about power protection circuitry. See you there.